Welcome to session 4, and this is our first of 2 lectures on log-linear regression. I'll start, as usual, with our learning objectives and outline. We're going to cover today log-linear models in the framework of generalized linear models, starting with situations that motivate the use of log-linear models and define the Poisson distribution and its use in the log-linear GLM. We'll identify applications and properties of the Poisson distribution and end with defining multicollinearity and giving some examples of it and the resulting issues. I'll start again with a brief review of GLMs and then go into this motivating example for log-linear models and introduce the Poisson log-linear GLM and end with multicollinearity. Recall those 3 components of the GLM. The random component was the part that can't be predicted. That's how for a specific value of the predictors that is conditional on the distribution or conditional on a particular value of the predictors, it's the distribution of the response variable. It was the binomial distribution for the logistic regression. It was a normal distribution for ordinary linear regression, and we'll be introducing some different random components in the next couple of lectures. And then the systematic component is that part that is predicted by the predictors, and that is this linear part. It's the betas. And then finally the link function, which is a function that relates the random component to the systematic component. And it can be either linear, it was the identity function in the case of linear regression, and it was the logit function or the log odds function in the case of logistic regression. In linear regression, the model looked like this, where individual values of y, where it was continuous, was equal to this this systematic compart, the expected value of y conditional on x, plus the residuals, or written out fully, it was this linear predictor, the betas times the predictors, plus the residuals. And the random component of y was summarized all of the assumptions of this model, where the residuals are independent, identically distributed according to a normal distribution with zero mean and a constant variance. And again here the systematic component was this linear predictor that's going to continue pretty much the same throughout the course, and in that case the link function was the identity link. In logistic regression, our model looked like this. The link function was logit, and the logit of the probability of a success of one of the outcomes that is also written as the log of the odds, probability over 1 minus probability, equal to this linear predictor. So the random component there is not written in terms of residuals, it's the distribution of the binary variable, the number of successes in a fixed number of of trials given by a binomial distribution. Systematic component the same, and in this case the link function, this logit function that converts probabilities to log odds. We talked a bit about additive versus multiplicative models, and recall that linear regression is an additive model because if we have the effects of independent predictors add to each other. So in an example with 2 coefficients of 1.5, if those binary variables are both equal to their indicator value 1, then it adds 3 to the expected value of y. Whereas logistic regression was a multiplicative model, whereas, so in that above example, if both of those indicators are 1, then it adds 3 to the log odds, so it actually increases the odds ratio by e to the 3, or about 20-fold. So that's the difference between a multiplicative and an additive model. So I'm going to start with a motivating example for why we need log linear models. In this example, I'm just going to introduce it here, and we'll explore it a little bit more during the lab session. But it's the effectiveness of a depression case management program. And in this study, this is an example from your textbook. If you go to this chapter in Wittinghoff, you can read a little bit more about it. But the research question is whether a new treatment can reduce the number of needed visits to the emergency room compared to the standard of care. And the outcome is the number of emergency room visits for each patient in the year following initial treatment. There are 4 predictors. Actually, there are more in the data set, but these are the ones that we look at in the examples in the book. They are race, white or non-white, treatment, treated or control being standard of care, the amount of alcohol consumption, which is a numerical measure, and drug use, which is a numerical measure. So we're interested in predicting this outcome, which is a count that cannot be less than 0. So there's some statistical issues in this data set. The first one is about 1/3 of the outcome variables, that is the number of hospital visits, are exactly 0, so they did not return to the hospital room at all. So it's definitely not normally distributed and not suitable for a linear regression assuming normal distribution, because we have a big spike at 0 and then everything is positive. It's skewed, it's definitely not normal, and there's no way to transform it to make it approximately normal either. And even if you do some kind of transformation like add 1 and take a log, there's still a lump at 0 and it's not anything close to normally distributed. There are other problems with a linear regression model on a transform value, that you could get negative predictions for the number of observations, which is obviously nonsensical. And finally, another challenge in this data set is that some subjects die or cannot be followed up on for the whole year, so we don't have the same length of follow-up for everyone. So it's for this issue, these issues introduced here, that we introduced the Poisson Loglinear generalized model, which starts moving towards being reasonable for a scenario like this. First of all, it is a multiplicative model, not additive. And so what that means is it will allow us to make inference on the ratios of mean emergency room usage. So the coefficients will be interpreted as ratios, like a coefficient of 2 will mean a doubling, not an adding of the number of emergency room visits. We will model the log of the expected emergency room usage, which will ensure positive means, and that's because the logarithm itself can be anywhere between -infinity and infinity, but the mean number is always positive, and you'll see what I mean by that, and it does not suffer from this log of 0 problem as a result, as in if you were doing a log transformation, you have 0 values. But we're not doing a log transformation, we're taking the log of the expected value, which is always positive. The random component of this GLM, the residuals, is still not going to be normal. That's where the Poisson distribution is going to come in. And there are other choices as well besides Poisson. So Let's write this down, the proposed model without time. This first bit here is a systematic part of the model. You can maybe recognize this by now. So you'll recall this part being the linear predictor, this part being the systematic part, the expected value of the outcome, and this being the link function. So you can start to see here where that name Loglinear model comes from. It looks just like our old linear regressions, except there's this log of the expected value. So equivalently in the second line, we're just taking the exponent of both sides. So you see how the expected value of the number of counts, in this case the number of emergency room visits, is equal to the exponent of this linear predictor. And I just want to emphasize this. I mentioned it once, but modeling the log of the expected value of y is not equivalent to modeling the expected value of the log of y. This would be an ordinary linear regression after a log transformation of the y value. So it would be like, well, taking a logarithm of your y values and then doing a regular linear regression. This is a link function. So it's a generalized linear model that has a link function other than the identity function. And this is an important distinction. And as I mentioned before, you can't in this case just take the log of y because we have 0 values. This, however, does not pose the same problem because the expected value of y is generally positive. Another nice feature of this model is that it can account for differences in follow-up time. So you remember that those patients were followed for up to a year, but some not for an entire year. So this can be accounted for by instead modeling the expected number of hospital visits per unit of time. And this is written down here. It's just a simple dividing the expected value by time, and it's equivalent to this just through your algebra of bringing out this log of t and then adding it to the other side so that it ends up on the right. So this term on the right hand side here is not it looks like a covariate like race, treatment, alcohol, and drug, but it's not. It's called an offset, and it differs from these in that it does not have a beta. There's no coefficient for it. So this is called an offset term, and it's a common feature in count models and in log linear models. So how does the Poisson distribution fit in? Well, that is the distribution that we use for count data in some situations like this. So it's nothing exotic. It's just a distribution like the normal distribution that you're familiar with, except that it has non-zero probabilities only for integer values. So this is 0 to 4. You'll see that it has data points here and just probabilities for the integer values. So this is the case. This is it has only one parameter. So whereas the normal distribution has a mean and standard deviation, this just has one parameter, lambda, and that parameter is actually equal to both the mean and the variance. So it's actually in a way even simpler than the normal distribution in that its mean and variance are the same, and that one parameter defines the entire distribution. So this case, this is the smallest, well, it's not the smallest you can have, it's the smallest integer you can have. You can have any value of lambda greater than 0. But with lambda equal to 1, you see that that probabilities of a count of 0 and 1 are about equal, and then it starts dropping off for larger counts. With lambda equal to 2, the probability of a 0 count goes down, the peak is up around 1 or 2, and then it goes down. And then for lambda equals 4, you see the peak up here around 4, and it's starting to look a little more symmetric and a little bit more like a normal distribution. So the Poisson distribution works in instances where you have count data, so you're counting the number of events, but where individual events are low probability, I'll say P for probability, but there are many opportunities, large N. So some examples would be the number of 911 calls per day in New York City, where there are millions of households that might call 911, but each one of them only has a relatively small probability. And I'll add to that the other requirement for it to work is that these events are independent of each other. So if you have on some days many households calling 911 but all for the same reason, that's not a Poisson distribution. It's where all of those individual events are independent. Or another example like this one, the number of emergency room visits. If you imagine that each day was an independent opportunity for something to happen that would require an emergency room visit, then and that it happened relatively rarely, but could happen independently each day, then the Poisson distribution would model that. Just as a note, the Poisson distribution approximates the binomial distribution in situations when n is large and p is small. That is, there's, say, at least 20 opportunities or 20 trials, and the expected number of outcomes is, or of successes is less than 5, or the expected number of failures is less than 5. And you can tell that it is an approximate fit of the data when the residuals of a model are approximately equal to the variance. So let's go ahead. So let's construct this GLM now with the log-linear link function and a Poisson error model. So we're going to model the number of counts per unit time as Poisson distributed, including this, this offset for link function, with the expected number of counts as lambda. So that looks like this. The expected value of y per time is equal to lambda I. So this is the parameter of the Poisson distribution, and it's modeling this as the mean of the Poisson distribution. I take the logarithm of both sides and add through that offset function, and then compare this to the systematic component of a log-linear GLM, or a log-linear link function in the GLM. So the systematic component of the GLM, using the equality we had before, has this log of the mean and variance parameter lambda equal to the systematic component, or alternatively lambda, the Poisson parameter, equal to the exponent of the predictors. So this is telling us now that the systematic component of our model is that the predictors give us this linear predictor. If we exponentiate it, it gives us the parameter of our Poisson model, and then we know what the distribution of counts is for this value of lambda. How do we interpret the coefficients here? Well, let's take one of the coefficients, beta 1 hat, and say that it came out to minus 0.5, and this is the coefficient for race where the reference value is white and the comparison category is non-white, then plugging this back into our remember that this was like lambda equals, sorry, I want to do a bit of drawing here. So this would be like a lambda equals and also a lambda equals for these two different subsets of our population. This top subset being the reference category white, and the bottom being the alternative category. Converting the addition and side exponents into multiplication, then everything here cancels out except for this one coefficient, and what it's telling us is that the ratio, so this would be lambda white over lambda non-white is equal to 1.65 because there's a coefficient of minus 0.5. So this is telling us that the mean rate of emergency room visits expected based on this regression is 1.65 times higher for white study participants than non-white study participants. All right, so just to write that out, again, that interpretation is that if this coefficient of race, beta 1, is equal to minus 0.5 and whites are the reference group here, then that means that after adjusting for treatment group, alcohol, and drug usage, that in this regression model, whites tend to use the emergency room at a rate 1.65 times higher than non-whites. If this were positive, then that would mean that the alternative group, non-whites, was using emergency room at a higher rate. Or equivalently, the average rate of usage for whites is 65% higher than that for non-whites. So it's this multiplicative interpretation of the coefficients. And these multiplicative rules apply for other coefficients as well, such as for continuous predictors, because they're exponentiated to estimate the mean rate. So if you have a, I don't know, age, well, no, age isn't a good example, blood pressure as a predictor, an increase of 1 unit of blood pressure doesn't just mean an increase of beta in the expected value of the response count, but it has to be exponentiated, or it can be interpreted exponentiated to interpret as a ratio. So that's actually all in this lecture about the Poisson distribution. It's, I think, conceptually in a lot of ways similar to linear regression and binomial logistic regression, but with this different distribution and link function. But in practice, you'll find a lot of things similar, and you'll get some more practice with it in the lab session and then in the assignment. So I'm going to talk a bit now about multicollinearity, which is something to be aware of for all kinds of regression. And it exists when two or more of the independent variables in your regression model are moderately or highly correlated. This can be high correlation among continuous predictors or high concordance among categorical predictors. And it impacts the ability to estimate regression coefficients in the form of seeing larger standard errors, meaning that those coefficients are unstable over repeated sampling. And you're also less likely to see a significant association between your predictors and the outcome because of this instability in large standard errors. And in the extreme case of exact collinearity, meaning that either that two of your variables are the same or that one of your variables is a perfect linear combination of several of your other variables, you might hear this sometimes called having a rank deficient model matrix or somehow a rank deficient matrix. But this is what that means. It's exact collinearity where one of your predictor variables is a perfect linear combination of some others. I just wanted to note this is also an issue in prediction models because it can lead to unstable or high variance predictions, meaning that your model changes a lot from one random sample to another, even from the same population. You can identify multicollinearity in a few ways. One is through pairwise correlation, either of your data or of your model matrix, the latter being easier to use if you have categorical variable. You can make heat maps, and you can use something called the variance inflation factor of the regression coefficients. And I'll give you some examples of these. This is a data set that's built into R. I'm just using it because I don't have to do anything in order to use it. If you want to see a little bit about it, you can just type $US judge ratings and it'll tell you a little bit of background about the data set. But in short, it's ratings that a number of lawyers gave to a number of different judges on different categories like diligence, oral statements, written statements. I forget what all of these things are. And I made this plot with this pairs function. If you just hit $pairs, you'll see the code that I used for this. It's also in the lecture R Markdown file. I just didn't show it on the slide here. But you see here some pretty extreme multicollinearity. So some of these, like say oral and written, are almost on a perfect straight line. This is in the opposite diagonal showing the correlations. That's a correlation, a Pearson correlation of 0.99. So that is real multicollinearity. And in this case, what does it mean? It means, I mean, there's a lot of it here. It means that the lawyers tend to give similar ratings on all of these different criteria. Either they rank them highly on all of them or low on all of them. They don't tend to give well, they really never give a judge a high rating for their oral output and a low rating for the written output. The one thing that is not correlated to everything else is this cont variable. I think that's the number of contacts they've had with the lawyer. So their ratings on all of these things are basically independent of how many contacts they've had with the judge. So this is some pretty extreme multicollinearity. If you saw this in your data set, you would really want to do something about it, like just removing some of these variables. Or there are a few ways you can deal with it depending on what your objectives are. Here's another example with another built-in R data set, the iris data set, which is petal and sepal length and width for several species of flowers. And in this, I just use this example because there's a species, which is a categorical variable. So I went and created a model matrix here just to make it easy to plot a heat map, and then I used this P heat map. I think it stands for pretty heat map, just because it's a simple, quick way to get a heat map, and I did it in black and white here. So by doing this, this is another way. I don't know, I think probably the pairs plot on the previous pages is maybe better. I just wanted to show you this anyways to show you how you can make a heat map. But you spot pretty quickly on here, so this scale is showing, again, Pearson correlations, with the darkest shade being 1 on the diagonal. This is each variable being 100% correlated with itself. And you see there are a couple of variables here, petal width and length, that are quite collinear, very highly correlated with themselves. And they're also pretty correlated with the sepal length and width. So basically, big flowers are big in all these measurements, and small flowers are small in all of them. The one exception here is sepal width, which does not seem very correlated with any of these other measurements. But these other measurements are pretty associated with the species Virginica, so this must be a large species, is what I take that to mean. Just so you know something about variance inflation factor, I fit a model here with all of the predictors and sepal width as the y variable, just because it's continuous, so I can do a regular linear regression. And from a fit model like this, and this also works for GLMs if you were doing a Poisson Loglinear model or a logistic regression, you can use this VIF function from the CAR factor, from the CAR package. And it gives you a simple little output like this, telling you the main column you're interested in here is this generalized variance inflation factor. These other ones, degrees of freedom, and this transformation of the GVIF. This gives you an indication of how much the variance of the coefficient for this variable has been inflated by multicollinearity. So we're seeing a large variance inflation factor for petal length. And if we go back to here, we see that petal length is one that is highly collinear with petal width and several other ones. So it makes sense that petal length has a high variance inflation factor, and then species is pretty high as well. If we were actually using it for a predictor as well, we saw it was also highly collinear with petal length. So there are a number of approaches you can take for dealing with multicollinearity depending on your objectives. One of them would be to just drop some variables and select a representative variable from your model. You can do this if highly collinear variables, it means that you're not getting much extra information by including them all, and you're creating an unstable model. So if there is some variable that just makes more sense, you think it is measured better, or it is there's some rationale for choosing one over another, you can just do that. You could average variables together. You could just create new variables that are the average of the multicollinear variables. You could do a principal components analysis or some other dimension reduction that will replace your original variables with these components that are orthogonal to each other. So principal components are never collinear with each other. They're actually completely orthogonal. And if you're doing prediction modeling, there are various methods that are developed to, among other things, deal with collinearity. Penalized regression, such as lasso and ridge regression, fall into this category. They are able to handle multicollinearity well as do other exotic machine learning methods like support vector machines. Let's wrap up. So in conclusion, log linear models are appropriate for data where your response is non-negative, it's 0 or positive, it's skewed, and it is count data, so it's discrete integer data, and where the probability of each individual event is low. The coefficient of any log linear model, whether it's Poisson or you'll be learning in the next lecture some other distributions for count data. These coefficients are multiplicative, so an increase in the in a coefficient has to be exponentiated to be interpreted as a ratio increase in your outcome variable, and the effect of two different independent variables multiply each other rather than adding. You can use this offset term to account for varying follow-up time or other reason where there's varying opportunity to be counted. Recall that the Poisson distribution is the limit of a binomial distribution when you have a high number of trials with the probability of success in each one being low. I want to just point out now that inference from log linear models, so the p-values and the coefficients and standard errors that you see in your model, is quite sensitive to the choice of this Poisson error model. And that is your assumption on the distribution of the residuals. And in the lab session, I'll introduce you to creating diagnostic plots on the residuals, so you can have a couple tools for deciding whether the model is a good fit for your data. And then next week we'll cover a few other options for when the Poisson error model doesn't fit, such as the negative binomial distribution and also zero inflation to the Poisson and negative binomial error distributions. Thank you, and I will see you in lab and see you next week.